Lesson 7-5, Modeling Data. Recall that linear, quadratic, and exponential functions grow differently, and we've looked at all of them. We've practiced graphing all of them. Linear functions are functions that have linear graphs, so straight lines. Quadratic and exponential, those are nonlinear, with exponential functions growing faster than quadratic functions. So here you can compare the three functions that we've gone through. Linear, it's a straight line. A line of best fit increases or decreases at a constant rate, so there is a specific slope. For quadratic, the curve of best fit decreases, reaches a minimum, and then increases, or the curve of best fit increases and then reaches a maximum and then decreases, depending on if it's a positive or a negative function. The data are symmetric about a line passing through the extreme point or through the vertex. And then exponential, the curve of best fit increases or decreases rapidly as it approaches one end of the domain and approaches an asymptote as it approaches the other end of the domain. You can use a graphing calculator to find a regression function, which is a function generated by an algorithm to find a line or curve that best fits the data. So calculators may also be used to compute a number called R squared, known as the coefficient of determination. That tells you how well that models the regression function. So an R square value that's close to 1 is an indication that is a strong fit to the data. So it's really, in other words, how accurate is your line compared to the data that is measured. So our first example, we want to graph a calculator. Use a graphing calculator to make a scatter plot of the data in the table and then determine whether the data are best modeled by a linear, quadratic, or exponential function. So to do this, we need to grab our calculators. To get to the table, we hit Stat, hit Edit, and if you have data in here, just hit Clear and hit Enter, and do that in both. And then L1 is going to be our table, or our X values. So I'm going to have -5, enter, -4, enter, -3, -2, -1, 0, 1, enter. I believe we have 2, 3, and 4. So 2, 3, and 4. Then the other side for our Y values, type in -3, -2.7, then we have -2.4, -2, -1, 0. Then we have positive 2.8, 8, 17.2, and 31. We just want to make sure we have the right amount in here. Now moving on to our second part. So we enter the data in here just like we did here. Part 3, we're going to make the scatter plot. So in our scatter plot, we need to turn our scatter plot on. So to do that, you're going to hit second stat plot, or your y equals. Go to our first one, hit enter. And then to turn that on, hit enter. And then we want to go to this first box down here. Make sure that the box is on there, hit enter. And then we have list 1 and list 2 here. And then we're going to change the Windows parameter on here. And we're going to use the ones that they gave us here. This is our X. So it's going to be -6 to -6. Sorry, -6 is your minimum. Your maximum is 6. And then the scale is 1. The minimum for Y is -10. The maximum is 40. And we're going to count by 5s. Then for here, you're going to hit zoom. And you're going to scroll down to number 9, or just hit 9, which is zoom stat. And I have to get rid of my line here, so I need to clear this. Now zoom stats. There's my scatter plots. Moving on to our next part. We have to determine if it's linear, exponential, or quadratic. So to do that, for this one, let's go back to my calculator here. We need to do the regression line here, but in order to do this, let's go to our stats. We need to calculate, and we need to test this out to see if it's linear. So if I do number 4, linear, and you see our r squared is 0.707. I can get closer than that, so I hit stat, calculate, let's do quadratic, which is number 5. Hit enter. This one is 0.957. So that's very close. What about exponential? Yeah, it looks like it's exponential based on what we have. So let's try stat, calculate exponential. It'd be number 0. Hit enter. This one's not giving me, the domain is off. So we'll bypass that part for right now. And since we know what the graph looks like, we know that this would be exponential. That would be an exponential function. Next part says use a graphing calculator to make a scatter plot of the data and then determine whether the data are modeled by linear, quadratic, or exponential. So based on what I see here, this could be quadratic, but let's test this out. We're going to go to our calculator. We're going to go to stats. Need to go to edit. And we're going to clear what we have here. And then enter our numbers in. So we have -6, -4, -2, 0. Then we have 2, 4, and 6. Going over, now we have -21, enter, -12, enter, -4, enter, and then 1.5, enter, 9, enter, 17, enter, and 25, enter. Now if I go to if I hit zoom, number 9, here's where our graph would look like. So based on what it looks like here, it looks like it could be linear. Now there is a way to determine if this is linear by checking if there's a slope. So we can use the slope formula there, or we can now just use our calculator. So if we do linear, number 4, hit enter. This says r squared is 9.997. So that's pretty good. Let's try quadratic. Number 5. That's 0.9975. Maybe I should write that down. So quadratic is 0.99751. I have to go back to the linear to see what that one was. Number 4. That was 0.99751. 0.9975108. I think that was the same. Let's see. Let's go to want to do that quadratic one again just to see if that's the same. They give the same numbers. So quadratic is 0.997518. So right now the quadratic is better. Now let's try exponential. See if the exponential one works on this one. So this was 0. Let me test. So for this one, we're just going to go by what the graph looks like, the scatter plots. So if I go to Zoom stats here, I was jumping the gun on that one. So this one, it looks linear, so we would consider this one linear based on what we see from the scatter plot. We will go through a little bit later on how to come up with the equation for it. So this one, use the graphing calculator to make a scatter plot of the data and then determine whether the data are best modeled by linear, quadratic, or exponential functions. So we're going to do this one. So we hit stats, edit, and we're going to clear what we have in here. So we have -2, -1, 0, 1, 2, 3, 4, 5, and 6. Then we have 3.8, 4.1, 4.0, 5.2, 8.8, 13.0, 21.3, 37.0, and 66.3. Now if we do zoom, number 9, zoom stats, that one looks exponential here. So we'd say exponential. Example 2, now we're going to model the data by using technology some more. We're going to use the graphing calculator to find the best fit model. And then we're going to use that model to predict the outputs when the input is 0, 22, and 60. The first thing we're going to do is enter our data into our calculator. So we hit stats, edit, move this over, clear everything. Okay, so we got 5, 10, 15, 20, 25, 30, 35, 40, 45, and 50. And then our Y values, we got 65, 140, 165, 185, 190, 155, 120, 70, and we have -15 and -95. Then we're going to go to zoom stat number 9. There, that looks like this would be a quadratic. So quadratic. So since this would look like a quadratic, let's do the regression. So stats, calculates, quadratic is number 5. Hit enter. Quadratic, you can see it's 0.994. So to write my equation, we would have y equals, and I'm going to round to the nearest hundredth. So this would be a negative 0.37 x squared plus 16.58 x plus 0.67. So since that's a rough estimate, I could use that formula there to do that, or we can do make this a little more accurate, let me round it to 3 decimal places. So 373 x squared plus 16.585 x and then plus 0.667. Now, if you want the most accurate number, then you would just put that into your calculator, substitute that in there. Otherwise, now if I go to my y equals and I hit vars, go to statistics number 5, go to EQ number 1, it puts the exact equation in there. And now if I hit graph, it will put my line through there, the best fit. Now if I hit second trace and want to find a value, so number 1, if I put a 0 in for x, let's see, second trace value, so number 1, let's put 22 in. I get 185.13. If I put a 0 in, it's whatever this would be. So if I put a 0 in, I would get 0.667. And if I put a 22 in, we got 185.133. And if I put a 60 in, so if I go to second trace, the value number 1, type in 60. I need to change my Windows setting here. So the Windows setting, I need to make this go to 70. Now graph it. Second trace, value number 1, if I put 60 in here, gives us negative 346.061. Okay, so here again, the scatter plots are going through those same steps again. Just a quick review. Determine the function of best fit. We saw that it was quadratic. You can do that by determining the r squared by hitting the calculate and choosing the regression type, which we did. Here you can use the table feature to find when 0, 22, and 60. We did it a little bit different way, but you can see these are the same answers that we had. Try another one here. Find the best fit model here. So we'll grab our calculator, hit our stat button, edit, clear what we have. So this goes from -3 to +3. So we got -3, -2, -1, 0, 1, 2, and 3. And on the other side, we got -7.5. We have a -10.3. You got a -12.15, a -14.2, a -16.16. Then we have a -18.3. Then we have a -19.98. We'd hit zoom number 9. I need to clear this part. So our graph here. Let me check something here. Yeah, this one should be a -14.2. There we go. Now we graph that. Here it looks linear, but let's just do the regression. So second, actually not second, let's do stat, calculates, let's try 4 linear. That gives us 0.96671, and the equation would be y equals negative 2.052 x minus 14.084. If we find that that's the best one. Stat calculates, let's see if it's quadratic. 5, 0.998. So it looks like it's quadratic for that one. But based on what our graph will look like, we're going to use the linear one. So if we use the linear, I'm going to go back to that. So stats for linear, enter. We're going to use this equation. So if I go to my y equals, I hit vars, number 5, statistics, go to EQ, number 1. And then if I hit graph, you can see that that matches up pretty well with what we have there. So we're going to use that equation. So this would be y equals negative 2.052x minus 14.084. Now we want to do the predictions when we have negative 8 and 17. So if I go second, trace, if I go to negative 8 would be 2.33. And if I did 17, scroll all the way down to 17, that would be negative 48.96. Those would be the exact, you might have a slightly different answer if you plugged it into this equation right here. But what we did on the calculator, that would be the exact answer. Next, consider the data shown here. We're going to find the line of best fit for this one and find out what the input would be with negative 4 and 10. We'll grab our calculators. Clear what we have here. So stats, enter. So we have 0, 1, 2, 3, 4, 5, 6, and 7. The other one, 148, 87, 43, 24, negative 2, negative 11, negative 11, negative 7, and 9. Now if we zoom number 9, I'm going to get rid of my equation here. Now this one looks like it could be quadratic for that one. So let's do the quadratic regression. So stats calculates quadratic is number 5. Hit enter. And we're going to have y equals 5.792x squared minus 59.958x plus 144.875. So if we do graph here, let's go to y equals, we'll hit vars. Number 5, statistics, go to EQ. Number 1, puts that in there, graph it. And we want to find out with negative 4 and 10. So second, trace number 1, the value. So we do negative 4. Let's see the windows. Let's make this negative 10. Now it should show up. So second trace number 1, -4. Hit enter. That gives us 477.375. So when we put a -4 in, it gives 477.375. And then if we do second trace number 1, now we put a 10 in here. Gotta change my Windows setting again. To maximum, let's make that 12 just so we can see it. Okay, now second trace number 1, 10 gives us 124. When we put a 10 in here, we get 124.458. Next, 40 years after opening their first shop, a popular coffee company grew over 17,000 locations worldwide. The table shows the number of shops in the years since the company began. Use the data to determine the best fit model, then use the model to predict the number of shops 10 years and 42 years after opening. So we go to our calculator. We'll go to stat, edit, we'll clear everything. Type everything in, so 0, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40. The other one we have 1, 17, 55, 116, 272, 677, 14, 12, 24, 87, 4709, 7225, 10,241, 15, 011, 16, 635, 17, 003. Now if I go to Zoom, number 9, Zoom stat, we can see our graph here. Need to get rid of my line here. So graph here comes up and then it looks like it's going to come back down over here. So if I change my Windows settings, let's go to, if I did 50 and then graph, oh. All right, so from here we need to find out, use the data to determine the best fit. So this one looks like it would be exponential. So let's see if we can get that exponential to work. So calculates exponential, which would be 0, enter. Okay, so the exponential here, so our equation would be y equals 0.6551 times 1.3175 raised to the x power. So if we're going to use that, let me go to my y equals, we'll hit vars. Number 5, statistics, go to easy, number 1, put that in there, hit graph. Okay, so it doesn't quite look as accurate, but that's fine. So second trace says 10 years, so find the value, number 1, we do 10 years. It tells us 10.322. So that would be about, so in 10 years, we would have about 10 shops. And in 42 years, let's check my Windows setting. Yep, that should work. So second trace number 1, type in 42. We would get, so that looks like 70,000 in there. So that would be roughly, yeah, so roughly 70,000 shops. And our last one, it is estimated the world population reached 1 billion around 1,804. Since then, it has increased. It has been increasing at a dramatic pace. The table shows the estimated world population in billions since 1900. Use a calculator to determine the best fit model for the data. This should not say coffee there. Now just go to our calculator. We need to go to our stats, edit, clear everything. And then we're going to type in 0, 50, 60, 70, 80, 90, 100, and 110. Then here we have 1.656, 2.558, 3.043, 3.713, 4.451, 5.289. And move this over a little bit. We have 6.089 and 6.892. And then clear this, then hit zoom number 9. Okay, so for that one, this one looks, if I were to expand this one, let's make this, actually if I did this 500 scale, let's count by 100s. Then hit graph. That one looks fairly like linear, but that is not linear there. This could be quadratic possibly, because we do see like it bends here. So let's do stat calculate number, let's do 5, see if it's quadratic. That one's a 0.997, so that one's pretty close there. So let's do that equation. So this would be y equals 4.822 x squared that'll be minus 0.0041 x and then plus 1.629. Now one thing, if you notice in the calculator, the a has an e to the -4th. That means I have to move the decimal place 4 places to the left. That's 1, 2, 3, 4. So that means I would have y equaling 0.123 and then I'll make that 48 x squared minus our b. We're going to keep that the same because there's no e's there, so it'll be 0.041x, and then it's plus 1.629. So that would be our function here. Now if I go to my y equals, hit bars, go to statistics, EQ number 1, enter, then graph that. That looks very, very close. So that's the most accurate one we have. Now if I hit second trace, 1903 is 3 years after 1900. So that would give us 1.6 billion. So we'll do 1.62 billion. If we did 1995, that's 95 years after 1900. Oh, second trace value, so 95. 5.59 billion. So 5.59 billion. Billion here, so we know what that means. And then our other one, 2020, so that would be 120 years after. So I'll check my windows. Yep, so we should have that. So second trace, number one, so 120 years after, we would get 8.08 billion. So 8.08 billion people. So that is our lesson on modeling data.